So good morning, everybody, and welcome for this new seminar from the Instituto de Astrofísica Andalucía in Granada, in Spain. And today we will have the talk by Frick Roelof from the Center of Astrophysics in Harvard and in Smithsonian. And he will talk about studying magnetic fields, dynamics, and fundamental physics near a black hole with current and future mm-VLBI instruments. So Frick will be introduced properly by. Okay, thank you.
Thank you very much, Rene. I don't know if your cam should be on. Yes. All right, so it is really for me a great pleasure to have you here, Frank. So Frank is visiting us during this week, and he is coming, as Rene mentioned, he's coming from Harvard for Center for Astrophysics in Black Hole Initiative, and we have been working with Frank for a long time. He is one of the most active members of the Event Horizon Telescope, and he's also working very actively in developing the new arrays, and in particular the next generation Event Horizon Telescope. He has been recognized with one of the EHT awards, and in particular the Outstanding PhDs award from the EHT for his numerous and very important contributions to the EHT. So far, he finished his PhD at the end of 2020 his PhD in Radboud University. His advisor was Heino Falke, and after that he moved to the CFA. Black Hole Initiative, as we mentioned before, and currently he is working many different aspects in the EHT and ngEHT. He is one of the best experts we have for VLBI data reduction, modeling of VLBI data, generation of VLBI data, and also he's actively participating not only in the Next Generation Event Horizon Telescope, but also in the Event Horizon Explorer, which is a space VLBI mission to observe black holes, to image black holes, to take movies of black holes, and so we are really honored to have Frank here with us today. So he's going to talk a little bit about everything, and at the beginning of the talk, he will show some of the results. And you may have seen that actually yesterday we published, and there was some press releases in Spain, in the US, and in Germany, basically all across the world, because we published the first circular polarization observations of black holes. In particular, circular polarization of M87, and Frank also published one of the extra paper as leading author with some of the modeling of the data. So he's going to talk about us today about this, and then in the second part of the ending part of the talk, he's going to present also the new projects from the EHT. So if people are interested in imaging and taking movies of black holes, so he's going to tell us about what are the next step in the study of black holes with mm-VLBI. So thank you very much, Frank, and happy to have you here.
Right, thank you very much, Mateo, for that very nice introduction. It's really great to be here and talk to you about these new EHT results that just came out yesterday. First, I'll just give a little bit of an introduction to the EHT in case you're not very familiar with it. So the EHT is this millimeter VLBI array with stations all over the globe that we've used to make the first images of the black hole shadows in M87 and Sgr A that I'm sure you've all seen. These two black holes are, the images look pretty similar, but they're pretty different objects. M87 is a 6.5 billion solar mass black hole in a giant elliptical galaxy 55 million light years away. And Sgr is our own black hole, the supermassive black hole in the galactic center, which is only 4.2 million solar masses. And an immediate consequence of this mass difference, which I'll come back to many times in this talk, is that the timescales associated with variations in these sources are very different. Because for a bigger black hole, it simply takes longer to orbit it, for the matter to orbit it. So for M87, we see variations in the emission on a timescale of days. In Sgr is much faster. It's variable on a timescale of minutes, and this gives us many headaches, but also some opportunities in the EHT analysis. A bit about the 2017 observations. Here you can see some pictures. We see there Pico, Veleta, nearby to here. I was here at the SMT in Arizona, and we're still working on some data from these observations and publishing about it. So this has been very productive observing campaign. So we're doing this together with the EHT collaboration, which has more than 300 members in 60 institutes spread across the world. Here you can see some pictures from our most recent collaboration meeting in Taichung in Taiwan. This is the whole group, and here you may see some familiar faces. Very nice group dinner with some of the European astronomers from the EHT. So back to the science, we are looking at these two main targets, M87 and Sgr A. If we look at lower frequencies than what the EHT observes at, we see that these sources are indeed quite different. For M87, we see this very strong jet being launched, and Sgr, we also see some larger scale structure at lower frequencies, but we don't see this jet. And we also know various properties of these two black holes to varying degrees, and that's sort of indicated with these colors here. So for M87, especially before the EHT observations, we didn't know the mass very well. There was a factor 2 uncertainty. We did have a good handle on the distance and the inclination with respect to the black hole spin axis, because we see the direction in which the jet is being launched. We still don't have a good handle on the spin of M87, and we have a bit of a handle on the astrophysical model, again, from the jet observations. For Sagittarius A*, the situation is different in that we know the mass very precisely, and we know that from observations of stellar orbits in the galactic center. Together with the distance measurements, this makes Sagittarius really an ideal black hole to do tests of general relativity, because the mass and distance together tells you exactly how large the black hole shadow should be on the sky. We don't see a jet, so we don't really know the inclination of Sagittarius A*, same for the spin and astrophysical model. And for Sagittarius A*, we have this additional complexity of the rapid variability on minute time scale, and also interstellar scattering electrons between us and the galactic center that scatter the radio waves, which makes the image a bit more blurry. With the EHT, we also observe together with many instruments across the electromagnetic spectrum. So here you can see a very nice multi-wavelength view of M87 going from the radio all the way to gamma rays, observing M87 at the same time. So we really get this beautiful complete picture of the black hole and the extended jet emission.
I have a quite minor question. So,
yes.
May I ask how accurately do we get the inclination angle information from the jet component? Uncertainty of that. So mostly say it is 165 or 50 degrees, but how accurately we can constrain the inclination?
It's a good question, and I'm not sure exactly what the uncertainty.
Observational uncertainty for the inclination. So in EHT, we simply use a specific value of the inclination angle, but I'm curious about the uncertainty of the inclination angle coming from the I don't know exactly what the uncertainty
few degrees. Few degrees, and also there is a dispersion in the jet, as you've noticed in the nature paper. So it's just, I would say, with uncertainty 4, 5, 10 degrees most.
Yeah,
I see. Yeah, thank you so much.
Okay. Also for Sagittarius A*, we had this major multi-wavelength campaign. So here you can see as a function of time, whenever these instruments were observing Sagittarius A*, the top row is when we had EHT observations of Sagittarius A*. And what's interesting is that here on April 11, right before the start of the EHT observation, there was a flare measured by Chandra in X-rays. So there was some big activity in the source there, and we are actually now starting up a new project within the EHT to see what we can see of that in the EHT data, and if we want to try to see if we can get a signature of these changes in the source. So how do we observe and make images with the EHT? We saw here the waves, radio waves coming in. They're recorded at each antenna individually. The data is written to hard disks, and these are then physically shipped to correlator centers, where per pair of antennas the data is correlated, and then there is a calibration process, and then in the end we can make an image of the source. So how does this imaging work with VLBI? Here we see the Earth rotating, and we see the baselines connecting the telescopes, and they light up whenever we had an observation of M87. In this plot, we see the length and orientations of these baselines plotted, and this is what we call the UV plane. And on each point in this UV plane, we measure a Fourier component of the source image on the sky. So the short baselines, so the short spacings between telescopes, give us information about the larger scale structure of the source, and the longer baselines determine the resolution of our instruments, and they give us the information on what the source looks like on the smallest scales. And combining that information, if we have enough of these measurements, we can make an image of the source. But in order to do this, because we always have some gaps in this UV coverage, we don't have the full information about the image. We always have to make some assumptions on the source structure before we can reconstruct an image. And I'll go back to that in a little bit. But first, I want to talk a bit about polarization. This is related to the results that came out yesterday. So the emission that we observe is synchrotron radiation. So this is coming from electrons gyrating around magnetic fields, and this emission is polarized in the direction perpendicular to this magnetic field. So if we make an image of our source in polarization, as you see there, this tells us about the configuration of the magnetic field. But polarization is also affected by light bending around the black hole, and also by properties of the accreting plasma. So together, the polarization image gives us a lot more information than the total intensity alone. And we've seen in the EHT that this was very useful in constraining our models that we fit to the EHT data. So we fit, or we compare our EHT image to these GRMST models of the plasma accreting onto the black hole. And with the polarization, we could rule out many more than with the total intensity data alone. What's also an interesting property of polarization is that it can probe the black hole spin. And we can see an example of that here. For a Schwarzschild black hole, also non-spinning black hole, we see a radial pattern in the polarization. And then when we increase the spin, the magnetic fields are getting dragged around the black hole in the frame breaking process. And then as a result of that, we get azimuthal magnetic field, and then the polarization is perpendicular to that. So we get a more radial polarization pattern for high spin black hole. And polarization is a probe of the accretion state. And by that, I mean the magnetic field flux trailing the event horizon. We can either have a mad configuration, that means that there's a lot of magnetic flux trailing the event horizon, or when there is not so much magnetic flux, we call that sane. And the difference between them in polarization is that a mad model gives us these very ordered polarization structures, and sane models would give us more turbulent polarization structures. Then in addition to this linear polarization, there's also circular polarization. Circular polarization is generated also intrinsically in the synchrotron process, and it gives us information about the strength and orientation of the magnetic field. And you can see example simulations here showing GRMHD model of the black hole viewed at two different inclinations, so from two different sides of the accretion disk. And we see that the sign of the circular polarization, which can be left or right circular polarized or negative or positive, indicated with the red and blue colors. And we see that the sign flips as you go to a different orientation. You can also hear in this cartoon, we see a typical helical magnetic field structure in the jet. And in these quadrants, the field is either coming in or out of the phase. And if we then look at GRMHD simulations that are viewed with this viewing angle edge on, we see also these different quadrants coming back in the circular polarization emission. But circular polarization, it's often difficult to interpret it like that directly, because it also depends a lot on the plasma properties. It's not just produced intrinsically, but also through a process called Faraday conversion. And this can happen through Faraday rotation. So this is the rotation of the polarization as light is passing through a magnetized medium, or by a twisting magnetic field geometry. So in short, the polarization, circular polarization also encodes a lot of information about the properties of the accretion plasma. Here we see an example of some GRMHD models drawn from our GRMHD library in circular polarization for a lot of different parameters. And the takeaway here is that you see a wide range of circular polarization structures, and also a lot of sign flips of the circular polarization within the same image. We can blur the GRMHD images to the EHT resolution to see what the EHT would approximately see when observing these models. And then we see that many of them are producing, when we sort of average over this more complicated structure, we see that many of them are producing simple structures that are dipoles that have right circular polarization on one side and then left on the other side. But the orientation of this dipole can vary quite a lot between models and samples, so it's not often easy to interpret. So what I've been doing in this project is try to approximate the source structure in polarization using geometric modeling. And this is a different process than the imaging that I talk about, because imaging is using a many parameter model, which are the pixel values of the image, with regularization constraints. And these are the assumptions you make on, for example, the smoothness of the image or the sparsity that you have to do to deal with this sparse UV coverage or incomplete sampling. But in geometric model, we impose the assumptions in the model itself. So we choose a geometric model that only depends on a few parameters, but that can still represent the emission that we see with the EHT variable. And this has some advantages. It will naturally give you measurements with error bars of parameters that we are typically interested in. For example, here a diameter of the ring or the thickness of the ring. And it can provide constraints even if there is not sufficient coverage or signal to noise ratio to do a full imaging process. And this can help in constraining the dynamics of Sagittarius star, which is rapidly varying. So for Sagittarius star, we have to rely on very short snippets of data, and using modeling, we can get some constraints, even though we have very little data at each given time point. We can use it to get information from sparse arrays where not many stations are observing, and also to get constraints on weak signals such as those in polarization. And it's also computationally very efficient. We can do everything analytically. So our favorite model to fit to the EHT data is what we call the M-ring model. And the M-ring model is just a simple geometric model. It's just a ring that's represented by this delta function. So this is representing a ring with a certain diameter. And then along the ring, we decompose an angular profile into Fourier modes. And these are weighted by these complex numbers, beta. And by adding more and more of these Fourier modes, we can make a more and more complex structure along the ring. And you can see an example of that here, where we have the 0, 1, and 2 mode. The 0 mode is just a flat flux here. The m=1, we can see one oscillation. For m=2, we can see 2. And then here on this line, we can see the sum of them. And it is also represented in this image. So you see, with just these few components, we can also already get an image that looks quite a lot like the image of M87 that you've seen. It's a bit rotated in this case.
A specific question. So
yes,
you provide the red and blue color component of the Stokes by Milky Way. And is it sufficient to use MG ring model to reproduce this kind of direction inverted feature?
yeah. So I'll actually talk about that in a little bit. Yeah. So we've extended this M-ring model to polarization, and there it works the same as in total intensity, with the difference that the image is now complex. So we have not only an intensity, but also a direction of the polarization emission. And what's especially interesting here is this beta 2 mode, because this is setting the twistiness of the magnetic field pattern. So for beta 2=1, we have this radial pattern. For beta 2=-1, we get an azimuthal pattern. And for the complex modes I and -I, you get this twisty pattern. So measuring this beta 2 mode will give us information about this magnetic field twistiness that, as I showed earlier, can be a probe of the black hole spin. We also extended this to circular polarization. So there the difference is now that the emission can be positive or negative. That is indicated with the contours, blue and red contours here. And here you can see an example. In this case, it's just a dipole with a 0 net circular polarization. Here we rotated the dipole. As you can see here, to -5 degrees, and we added a net circular polarization of 5%. So the red part is a bit brighter. And then here we've added the beta 2 mode and circular polarization to make a more complex structure. So this is just an example of how you can build up a Stokes-free structure.
Sorry, but your GRMG model provides like outer component is the red and the inner component is blue. So in this case, yeah, I think EHT resolution will blur as this kind of inverted inner and outer feature. But do you your model also follows this kind of inverted outer and inner feature?
Yeah. So if you really have a structure that has an outer positive and an inner negative ring, that is more difficult to reconstruct with just this model. But what you could do in that case is take 2 of these M-rings and fit them, one with a smaller radius and one with the larger radius. Try to approximate the structure like that. Yeah, but I haven't tried it before. I've only used the single M-ring models so far. Yeah. Okay, so let's apply these methods to some EHT data. So here we see on the 4 days that EHT observed M87 in 2017, April 5, 6, 10, and 11. The average image that was already published by the EHT in linear polarization, where we see this beautiful twisty pattern. And now we fitted our M-ring model in polarization to the same data sets, and then these are the results we got. So in the middle row, we see the posterior maximum of our fits to the same data, and then the bottom row, we blurred these fits to the same resolution as these images were blurred, so we can compare them more directly. And you can see already by eye that the structure that we get with the M-ring model is very similar to what we get with the imaging approach. So even though we're only using a few parameters, we can really approximate the structure in linear polarization quite well. Now in circular polarization, we need to take a lot of care in the data products that we're fitting, because circular polarization is a very weak signal. It's usually a percent level signal, and we have to be very careful with our data calibration and data products. So don't try to understand all the details of this if you don't work with VLBI data every day, but I'll try to go through it a little bit. So each antenna of the EHT records in left and right the circular polarization. And then we correlate the data per pair of antennas. So then we can form these four correlation products. We can have left-left, right-right, left-right, or right-left. And the circular polarization information that we are after is primarily in the parallel hand visibilities, as we call them. So this left-left and right-right, you see them written out here. Don't look at all the terms, just see that right-right depends on I plus V, so the total intensity plus the circular polarization, and left-left depends on I minus V. And using these data products, we can form data products that are invariant to many of the calibration issues that we have in the EHT, such as those from the atmosphere. And what we can do is take the ratio of these right-right over left-left, because then our atmospheric fluctuations cancel out, and we are left with something that's written here that depends on the Stokes V, and only on the ratio of these G terms. These are the antenna gains that can be quite uncertain, but the ratio of them is usually quite stable, and we have a decent handle on them. So that makes this right-right over left-left data product a useful data product, although there is still some calibration uncertainty due to the gain ratio that we know pretty well, but not very well. Another thing we can do is use closure quantities of these parallel hands, and these will be fully independent of these right and left gains. But we pay a little price for that, in that there is a bit less information in the closure quantities than in taking the full ratio of these correlation products. What are these closure quantities? So these can be closure amplitudes and closure phases. I'm just showing closure phases here. It is the sum of the visibility phases, so the phase of this Fourier component, measured across a closed triangle of baselines. And when you sum up the phases here, the data corruptions at the individual stations, they drop out. So here, for example, they can enter with the plus sign, but then on the other baseline to the same station, they enter with the minus sign, and they cancel out. So this is really a very robust data product that we can use to get information on our source structure. If you measure a closure phase on a triangle that is deviating from either 0 or 180 degrees, you know that you're looking at a source that has some intrinsic structure. So it's not just a symmetric plot on the sky, but you know that you're measuring some more complicated structure. That is the case for total intensity. If we now look at circular polarization, we have to look at the differences in closure phases between these right-right and left-left visibilities. And if we see non-zero differences there, then we know that we have detected some circular polarization structure. Here you can see some examples of that. I won't go through all the panels here, but if you look, for example, at this top left panel, I put in an M-ring that has some asymmetric structure in the total intensity. So it's brighter on this side than on this side. So we have non-zero closure phases that also change as a function of time. But the closure phase differences between left and right are completely consistent with 0. So we're not measuring indeed any circular polarization here. Looking at this model, which has the same structure in total intensity, but I've added here a circular polarization component that's also asymmetric, we see that we start to see differences between these right and left closure phases. Here you can see that they are significantly non-zero. So if you see something like this, you know, okay, I've measured some kind of complicated circular polarization structure. Even though from this you might not know exactly what it looks like, you know that it's definitely there. And this is exactly what was the main result that we published yesterday with the EHT. So here you can see measurements of these closure phases in the parallel hands on this triangle from ALMA in Chile to the SMT in Arizona to the LMT in Mexico. And we see here on all the observing days and the frequency bands that the EHT observes in, we see that the closure phase differences are significantly non-zero. So from this we know that we have detected some circular polarization structure on scales of the event horizon in M87. And we were quite happy seeing this because it was really not a given. We're looking at the percent level signal, and you can see that here in this plot, which shows the signal to noise ratio of the circular polarization on our different baselines. That is indicated with the colors, and the gray points indicate the signal to noise ratio of our total intensity. So you can see there can really be 2 orders of magnitude differences here. So we're really looking at a very weak signal, but we managed to tease out a detection of the circular polarization structure.
Can I ask one?
Yes.
Minor question. So there is a slight difference between the low band and the left band in left and right panel. And is there any possible reason for the a little different morphology to the time direction?
Well, I think that this is probably the consistent within the error bars. I don't think these are very significantly different.
I see.
Yeah.
Yeah, I'm curious about the slope of the RR and L difference between L1 and I1.
Yeah.
Yeah. We signal is too small. So yeah.
Yeah, that would be interesting if we would see something like that. But yeah, I don't think we can conclude that from these observations yet. So now that we have detected the circular polarization structure, the next question becomes, can we actually make an image of the circular polarization structure? So to answer that question, we first looked at some synthetic, so simulated EHT data. So we took a GRMHD model that you can see here in linear and circular polarization. We simulated EHT observations of this model with the same properties as the EHT observations of M87 in 2017. And then we tried to reconstruct these structures with a lot of different methods developed by different people in the collaboration. And we can see here the results for the linear polarization. So all these, the columns here show all kinds of different imaging methods for the linear polarization. And on the far right is our M-ring geometric modeling methods. So you see in linear polarization, all these different methods agree with each other quite well, and also do quite well at reconstructing the basic properties of the ground truth model that we put in. If we now look at circular polarization, the pictures looks quite different. You see that there are more significant differences between the structures reconstructed by the imaging methods, and we also see that not all methods do very well at reconstructing the ground truth source structure. The M-ring model here we see does pretty well. We only allow a very simple structure here, a dipole structure, so it's what we call M=1, but it gets the overall orientation of this structure that is in the model quite well, and it also did well on some other synthetic data sets. What we see in this plot is the absolute circular polarization fraction averaged over the whole image. And then the stars are showing the ground truth values for 3 different models. The panels that you see on top here correspond to data set number 2. And then in the different colors, we see the recovery of the circular polarization fraction by our different methods. And we see that most methods do pretty well when we have a relatively high circular polarization fraction of a few percent, here 3.5%. But when we go to very low polarization fractions, we see that there's quite a lot of spread in the recovery from the different methods. But the Emring model, because it restricts the source structure to simple structures, does quite well, even here to a sub% signal in circular polarization, where the imaging methods have a bit more trouble. So let's see what it looks like when we apply this to real EHT data. So here we see the same methods applied to the EHT data on April 5 and April 6 at the 2 different observing bands. And here we see, like for the synthetic data, that the structures that are recovered are quite different between the methods, also between the different days and between the different observing bands. So this is telling us that even though we do see circular polarization signal in the closure phases, we cannot make a robust image of the circular polarization structure yet. And we see similar results here on the other days, April 10 and 11. What we could do from this analysis is establish an upper limit of this result circular polarization fraction of 3.7%. And this upper limit we saw is actually consistent with our GRMSD simulations, and it's favoring these MAD models, which had a coherent structure in linear polarization. And these MAD models were also favored by the linear polarization observations of M87, and they're now also favored by the circular polarization observation. So this is an independent way of verifying that the MAD models are really preferred here by the EHT data. We also see that the dominant production mechanism for the circular polarization is Faraday conversion. So what we see is not circular polarization that was generated intrinsically in the synchrotron process, but it's been generated through all these plasma propagation effects. Going back to the images, what stands out is that in contrast to the imaging methods, our geometric modeling methods are consistently between all the days and between all the bands, also on the previous 2 days, showing the same structure with more negative circular polarization in the south, close to the peak of the total intensity. So that's quite an interesting result that we'll look into a bit deeper. So here we see our Emring fits either to these closure products or the right of left visibilities. And we see that no matter which data product we choose, we get approximately the same structure for all the days. We can now challenge the model a bit more. So here we only allow dipole structures, nothing more complicated than that. But now we go from m=1 to m=2. So in principle, we now allow also quadruple structures, but we see that still our data prefers to see this dipole offset between the south and the north region of the image. We can go even further to m=3 to allow even more complicated structures, but there we see it starts breaking down a little bit. We start to see more variation between the structures, except for April 11, the last day of EHT observation. We see we still get this dipole structure, and this was also the day that we had the best coverage, the most data for M87 with the EHT. So it really seems to be preferred there. So what can we conclude from this all? We have detected circular polarization, but we could not reconstruct a robust image. However, with simple geometric models, we do get a clear indication of a certain north-south asymmetry being favored by the data. But we have to view that result with some caution, given the difficulty that the imaging method saw in reconstructing consistent images, and because of the structural assumptions that we imposed. We saw before in the GRMHT simulations that I showed that a very complex structure on small scales can lead to this dipole structure at EHT resolution. So the underlying structure may be much more complex than just this dipole. But I'm pretty positive in that with a bit better coverage and sensitivity, we will actually be able to make those V images. I think we're pretty close to that, given that we've detected it and we've seen some clear structural indications with the modeling method. So in the remainder of the talk, I want to talk about what is next for the EHT. And I think one of the most exciting topics that the EHT will tackle in the coming years will be dynamics of the source. So we've now produced static images of this black hole, but we want to see how things change, how the plasma behaves when it falls into the black hole. For M87, because it's this bigger black hole that varies more slowly, we will need really multi-week movie campaigns with a high dynamic range, so that we can see not only this black hole shadow, but also the jet being launched at the same time. For Sagittarius star, we will need a very high time resolution. We will need a sub-hour time resolution to capture the rapid variability. And both of these can be accomplished by extending the EHT with more stations. So we can fill in the gaps in this UV coverage, and that will help us getting the dynamic range we need to image the M87 jet. And it will also help us getting more snapshot coverage, so we can start to reconstruct movies of the rapidly varying Sagittarius star emission. And we are already working on this. We're expanding the EHT. So in the red sites here are the ones that observed in 2017. The three yellow sites here are have already participated in later EHT observations, and there are also concrete plans to build an additional telescope in Namibia. And you can see here in this plot the black points showing the UV coverage in 2017, and the colored points are all the new baselines we get with these 4 additional stations. So you can see we are already filling a lot of these gaps. And to answer the question, what can we see when we have these additional stations, we have to generate synthetic data. This was a large part of my PhD, was developing such a synthetic data generation pipeline, where we put in a lot of information about the instruments itself, but also we put in an atmospheric model, so that you can put in some weather parameters, some weather conditions, and calculate the effect on the measurements. And what we also put in are pointing offsets of the antennas, because they're not always pointed directly at the source, but they will be offset and wobble around a little bit. So that's also an effect we have to take into account. In addition to that, you also need to specify the telescope location and observation schedule, and then we can generate this EHT data as it would come out of our correlator, and then we pass this through an actual EHT calibration pipeline to get a data set very similar to the one that we would analyze with the actual EHT. And you can see here, we applied this synthetic data generation pipeline on this model of M87. And here with the 2017 array, we see a similar ring structure that we have indeed observed. And then we when we add the 4 extra stations, we see that the image was sharper enough, and we can see some first hints of this extended jet structure of M87 that we want to see. We want to see this jet being enlarged from the black hole. Also, this will help a lot with imaging cellular star and making movies of cellular star. So here's an analysis done by m87 who looked at the influence of adding stations in Africa, the African continent, to the EHT. So these are the AMT in Namibia, but also a station on the Canary Islands. And here we see a plot of the UV filling factor. So that is a measure of how much of this UV plane is filled with baselines. And we see that when we add these 2 African stations, we get a lot of extra filling factor in this eastern part of the array. So that will allow us to observe cellular star much longer with much better coverage, which will help reconstructing movies. And then we also showed here that we put in a model of a hotspot orbiting the black hole with this extended EHT array with even image something like that. But we want to go much further than this. So we are now developing the next generation event horizon telescope, which will be a huge extension of the EHT with about 10 new sites added. We will have simultaneous observations at 86, 230, and 345 gigahertz, a 5-fold increase of the data recording rate, and extended observing mode. So right now with the EHT, we observe only 2 weeks per year, so it's hard to do this long-term monitoring of the M87 jet, but with the ngEHT, we'll be able to observe much more often. And you can see here the very dense UV coverage that this extension will lead to. So to answer the question, what can we see with this extended EHT, the next generation EHT? I'm now running the ngEHT analysis challenges. And what we do here is we start from some ground truth source model, we simulate ngEHT observations, and then we publish those simulated observations on a website, challenge.eht.org, where people can download them and analyze them, and then we compare the results to each other. And you can see an example here of a submission by the team here at IAA of the M87 jet. So we're doing this to help develop science cases for the ngEHT, but also to identify strengths and weaknesses of different analysis algorithms. And we've seen that it already has led to development of these algorithms. People are using these datasets to make improvements on their analysis methods. And it's really a broad community project. We have experts on the theoretical modeling, on the data analysis, but we also found that it's useful for people who are just getting started on VLBI to work with these synthetic datasets and reconstruct these beautiful ngEHT images. So if you want to get started with VLBI analysis, this would be a good place to do that. I'll just show a few highlights of our challenge results. Here we simulated a movie of M87 and weekly ngEHT observations of this movie for 5 months. And here you can see as a function of time for different methods what they reconstructed. I will just highlight this one here, which did very well, which is the resolve Bayesian imaging algorithm. And you can see here you get these beautiful reconstructions of the M87 black hole shadow and emission even far out into the jet. And these are large scale images. So these are really very high dynamic rates. Yes.
Sorry for many questions, but it is quite interesting because 5 months of observation requires expected observation in summertime. And typically, in my view, the summertime provides a large opacity and and which provides a little noisy of the image reconstruction method. But this image is quite beautiful, and there is no frame-to-frame difference between the early time and the summertime reconstruction.
Right.
So
so
is it coming from the dynamic reconstruction advantage, or simply coming from the great UV coverage with ngEHT?
Yeah, so a lot is just from the extra UV coverage that you get. I'm not sure if we actually included the varying weather parameters across time here or not. I would have to go back to see if we actually did that.
Yeah, but if the weather condition are correctly included, it is quite beautiful.
They're at least the weather conditions are at least the correct ones for April. I have to check if I actually did vary them across different months. But yes, with ngEHT coverage, you can really. This was all generated with the Simba pipeline, so it really had all these observation and calibration effects included. So yeah, I was also quite pleasantly surprised with some of these reconstructions. They're really good. Yeah. We also included models for Sagittarius A*. So here we can see a hotspot that is forming and then shearing out as it orbits. So here it makes a full orbit within just 1 hour. And we again did the same thing with the simulations of the ngEHT observations. And here on the right, you can see a comparison. This was done by Antonio with EHT 2022 coverage and ngEHT coverage. And we see with EHT 2022, we can see this emission ring in the reconstruction, but we don't really see the orbiting hotspot. But with ngEHT coverage, we do see this hotspot being formed and sharing out within just 1 hour, thanks to the additional UV coverage here. We also added in polarization. So here is just an example by Justin Vega, who was my undergraduate intern at the CFA, who did some polarization reconstructions, and you can see you can recover the polarization structure here up to far out in the jet as well. And we're now running challenge 4. I won't go into much detail about this, but here we want to focus more on parameter extraction rather than just imaging. So if you're interested, this is something you can still participate in. And in parallel to this, we are running the ngEHT forecasting tournament, and this is a social science experiment. It will be the first kind of its kind in astrophysics, and this is open for everyone to participate in. And here people answer quantitative questions about the ngEHT, what it will look like, what it will be able to measure, and what people predict for the ngEHT to measure. And then people talk about this in small groups, and then we run the same survey again, and we see how people's answers have changed as a result of the discussions. And we can do multiple rounds of this so that we sort of track the group thinking on several of these questions about the ngEHT and the science that it will do. And that will be helpful in identifying unresolved ambiguities that sort of live within people's minds in the collaboration, and can hopefully in the end lead to a more focused research effort. And this is now also running, so everything has been posted on the ngEHT Slack. If you don't have access and are interested in participating, please let me know, and I can send you the link. Now, after this, ngEHT will be done imaging black holes. I think the answer is no, because there's still a lot to do in space. So after the ngEHT, we will be done on the Earth, because we are really limited by this limited size of the Earth and the atmosphere, which make observing at high frequencies very difficult. But we can make extensions into space. So in space, observing space satellites, you can make much longer baselines and observe at higher frequencies because there's no atmosphere. And there is really unique and exciting science that is only accessible with a space array and not from the ground. So I've been involved in the development of 2 of these space VLBI array concepts. One is this event horizon imager, which is just 2 or 3 satellites in circular orbits at slightly different radii. So you can see here as they orbit the Earth, they slightly drift apart. And as a result, in the UV plane, you get this dense spiral structure. So we measure basically all the Fourier component of the image up to a resolution of down to 3.5 micro-arc seconds. To give you a comparison, the current EHT resolution is about 23 micro-arc seconds. So that's really a huge resolution boost. And you can see here that with such a configuration, you can make really very sharp, beautiful images of the black hole. We do see that this concept is limited by the signal to noise ratio. So we ideally want big dishes. This is, however, quite difficult to do in space, to launch a big dish that can observe at these high frequencies. So maybe we have to do something like this, where we have an array of small dishes together, and then you can make these really sharp images where you can see this thin photon ring that is encoding a lot of information about the black hole spin and can be used to test general relativity. And here you can see the movie reconstruction with this concept of M87, the ngEHT model. And you can see here the ngEHT input model and the reconstructions are almost indistinguishable from each other. So this is would really give a huge boost in imaging. But it's difficult to do this technically. There's some technologies needed that are not fully developed yet for space applications. So there will have to be some technology demonstrations, very small missions in space before something like this could launch. But it's a very promising, exciting concept. Now, there's another space VLBI concept that is called the Event Horizon Explorer. And this will be just a single satellite extension of the ngEHT. So it will observe together with the ground ngEHT stations. And the aim here is to measure this thin photon ring that we call the n=1 photon ring. This is where light has made a full U-turn around the black hole, and it's lensed by the black hole into this very narrow ring. If we can measure that, we can measure the spin of the black hole accurately and do much more precise tests of general relativity. And you can measure this when you go to long baselines around the geosynchronous orbits, because then all the larger scale structure is washed out. But you do see this typical ringing that is caused by this thin photon ring. And if you can measure this pattern, you can measure its properties. And this is currently envisioned to be a NASA mission, a medium explorers mission with a budget of around $300 million, with a 3.5 meter dish in a geosynchronous orbit, and it will observe at the same frequencies as the ngEHT, and can, as I mentioned, give us measurements of this thin photon ring. And this is a collaboration with mostly US institutions at the moment, but it's still open to other international partners as well. So that brings me to the end. So I think we have an exciting future ahead for millimeter VLBI and black hole science, and the EHT images are certainly not the end, but there's the beginning of many more developments. Thank you.
Thank you very much. That was very comprehensive. You're touching many different aspects, from imaging to movies to space VLBI. Wonderful. So, questions or comments from Craig?
Yeah. So Very nice talk. Really, really, really nice. You were showing some like testing, right, of like this 5 months period where you would observe M87 every or weekly or something like that. So how would you do that? Like, how would you coordinate like all of these telescopes? Turn on into VLBI modes every week? Like, is this something that have been talked about?
Yeah, so that's a good question. So what I simulated here is indeed, I think, a bit optimistic because I really simulated the full EHT plus ngEHT array observing every week. But with this, the ngEHT will build many new stations. So these will really be dedicated to this project. And we may not need the full array at every time to still be able to image the source and the jet. And we, for example, the EHT now uses ALMA, which is a very, very sensitive station. But also if we use other sensitive stations like the LFT in Mexico or the NOEMA array in France, we can use those as anchors and still get very good image quality. Yeah.
When is the African millimeter telescope scheduled for operating construction and so on?
I'm not sure exactly, but there's been a lot of developments in the funding, so there's a lot of funding for it now. So I would say within a few years, yeah, in principle, it should be possible. But I'm not sure. I'm not very involved in it, so I don't know the exact timeline.
And the idea with the ngEHT is not to rely that much in ALMA as well, right? It's like
Yeah.
So you can trigger observations without having to go through all the ALMA proposal system.
Exactly.
And so on, right?
Yeah. So we'll have dedicated ngEHT stations that we can just use.
Greg, in the circular polarization observations of M87 for 2017, the paper just came out, I guess there were some indications of a changing ratio between the two circular polarization over time. Did you model that? Or did you try to model? Do you have enough signal to see any possible variability in circular polarization in your modeling of the data?
No, I haven't really looked at that. Well, I've done the modeling for different days, but I think the uncertainties there are still too large to say anything about variability. Yeah, the dipole structure is already a bit uncertain. So I think for variability of circular polarization, we really need to get better data. Yeah.
At the beginning of the talk, you showed some quantities for both M87 and Sgr A that have been answered and well known previously, but the PhD started answering some of these questions, and many of these are still not answered. At what part of the new development in arrays and also pipelines can we expect to answer some of these questions, like ngEHT, the phase one, or do we need space VLBI to answer a particular question?
So I think with ngEHT, we will be able to answer some question about, for example, the jet launching of M87. We should be able to see that very nicely. We should be able to make movies of Sgr A. And that will help constrain plasma models there as well. Where we really need space is the high precision measurements of fundamental parameters, like the black hole spin, for example. We could get a handle on that with ngEHT, for example, from the polarization pattern and the variability. But to really make very high precision measurements of black hole spin from the photon ring, that's something we really need to go to space for.
Can we also expect looking at other targets other than M87 and Sgr A? Because
yeah, definitely. Yeah. So for the ngEHT, I think it's planning to look at a huge sample of targets, and I think at least of the order 10 of those should be imageable. We should be able to see a black hole shadow at 345 gigahertz or so, or at least measure its properties. Yeah.
I want to know, because the EHT have very long baseline, so must have very high resolution.
And does it mean that we only can observe very strong and bright source and we can't observe weak source?
Well, we have so the weaker source that we can observe is determined by the size of the dishes, and we have, for example, ALMA in there, so we can have quite sensitive observation. So we're not very strongly limited by sensitivity at the moment with the EHT. The stronger limits is on because of the sparsity of the image. So the number of stations we have, that's the most important bottleneck.
So is EHT now only observing very strong source like M87 and the signatures?
Yeah, so the reasons that we observe those sources is not that they are particularly very strong sources, but it's because they have the largest angular shadow on the sky, and so those are the sources where we can actually image the full black hole shadow.
Oh, I see.
Yeah. Have you tried hybrid modeling and imaging like it's Amy's? Do you think that it would go to 345 gigahertz for M87? Would it be possible to constrain in one ring with EHT observations?
It might be. It could be tricky, because it's it's a really high resolution signature. But for example, Daniel Palumbo has done this work for polarization, showing that on ngEHT baselines, you could see the signature of the polarization pattern that flips between the n equals 0 and the n equals 1 emission. And that is something you could just see in the visibility domain. You will see a flip of this this beta 2 observable. But to make an actual image of the ring, I don't think we could. I don't think we could do it. ngEHT in the 345, but with some modeling we can maybe get some information.
I'm not sure I understood everything about the closure phase and everything, but like you seem like that, or what you showed is only like one of the triangle, let's say, like 3 stations, and you calculate the closure phase from there, and then but is it from only these 3 stations, or you tried it from other?
Yeah, we looked at all the triangles, but it was only this triangle where we saw this clear difference between the right and left.
Okay. The other ones, like I guess I don't know, the signal is not good enough, or like what?
Yeah.
Like, okay.
Yeah.
So like only those 3 you could do that.
Yeah, exactly. That's where we saw this clear difference.
One quick question. Is Simba available online? And is there a tutorial for us to follow?
Yeah, it is online. You can download it. There is some tutorial from a very long time ago, but I can pull it up. It has a little bit of learning curve because there's many parameters that need to be set, but in principle it's all available if you want to use it.
I want to know, as for the space VRB, you mentioned about 3 new telescopes in space, and the gap of each telescope is really slight. Why we don't put a larger gap?
So show this movie again. Yeah. So you see, with a slight gap already after a while, we get a very large distance between some of these telescopes. So even if you have a small gap, the resolution is really determined by the size of the orbit itself and not by the gap. What you can do is play around with the size of this gap, and it will mainly set the time scale it takes to go from the shortest to the longest baseline. So if you put them very close together, you get a very dense spiral structure. If you would put them further apart, you will get a less dense spiral structure, which maybe only has a few orbits here, and then it reaches the longest spectrum. And that can be helpful for some sources where you want to image variability, for example, where you want to more quickly fill the UV plane, even though it's less dense.
Yes, it's maybe I see.
You can resolve the variability.
Yeah, but here you didn't put the ground space baselines.
Right, this is
Also,
pure in space.
if you add the ground space baseline, you will get instantaneous even much better.
Yeah, that could help with it. Yeah. Well, this is observing it a very high frequency, so that is difficult to do from the ground for a long time. But yeah, I think in principle, something like this we should definitely do. Like some kind of hybrid where we have a high frequency mode for space and then at the 230 or 345 receiver to do observations with the ground.
Yeah, you can put the satellites farther apart, but then you have the issue also the communications. Nowadays we are trying to have optical communications or high signal to noise data for large bandwidth. You put it farther away, then the communication it's going to be a lot less reliable. And then also if you put farther away, the coverage of the filling of the UV coverage is going to be a lot slower. So, for instance, for site A, we wouldn't be able to get, minute scale movies like on the upper EHT and things like that. But there's a lot of very interesting science on there.
Isn't there like a problem to send the data? Because right now you have to ship the data.
Right. Yes. Yes. Yeah. No, we're not going there with rockets to get the.
We can send the students. Collect the data, break it down.
Yeah, no, so that is indeed an issue. So you would either need a very high bandwidth data downlink. What we looked at with this coverage, this configuration is to do the correlation actually on board. So we would have the data sharing between the satellite, then do the correlation on board before sending it down. Yeah.
Okay, so thanks a lot, Frank.
Oh.